They saw the different types of tricky things with mechanisms, either the fast equilibrium. Everybody is here and stay. Welcome, welcome everyone. Sorry for that little tech blip. Looks like everybody is here and stable now. So we are going to get started. When we last left our heroes, they had conquered the kinetic section. They saw the different types of tricky things with mechanisms, either the fast equilibrium method, which is what you use when, of course, the equilibrium is fast. And that's when we use the equilibrium constant, isolate for an intermediate, and then sub that into the initial rate. We contrasted that against the steady state approximation, which has a lot of the same attributes. In this set as well, you still use the second, or I guess the last step. And then you still want to isolate for the intermediate, but the difference is in how you isolate for the intermediate. The steady state approximation actually makes no assumptions about the speed of the generation of this intermediate. So it's a little bit more general, and I'd say it's more generally useful as a result of that. What we did then was we wrote out all the different ways that we could produce the intermediate and the ways that we could consume the intermediate, and living up to the steady state name, we said that the rates of those are going to be equal, because if you produce something and consume it at the same rates, you're going to have a steady state concentration. Then, just like before, we isolated for the intermediate and sub that into the initial rate law. So the only difference in those two methods is this step 2 with how we're going to figure out the concentration of the intermediate. In the rapid equilibrium method, we use the equilibrium constant, whereas in the steady state approximation method, we write all the ways that we produce and consume the intermediate. And I know I'm belaboring this point a little bit. I know I'm going on and on a little bit, but this is like almost guaranteed on your final. And the steady state equilibrium, the steady state approximation is worth a bajillion marks. So it's super, super important to lock down. 3 marks. All right, so we ended last session having looked at oxidation numbers. We learned the ways to assign our oxidation numbers. We learned that the sum of all the oxidation numbers combined is going to be equal to the overall charge. We learned that elements want their column's charge. And we saw that with this diagram. Then we wrapped up last time by assigning some oxidation numbers. I want to make sure that we have these locked in, so please also assign the oxidation numbers for carbon, hydrogen, and oxygen in the reactant side of part B. Good luck. All right, fantastic. Let's take a look. For carbon and hydrogen, what do those like to be? Hydrogen likes to be +1. Carbon can be either positive or -4. And in fact, carbon can kind of do anything. It's pretty flexible because it does have, it can go in either direction there. As a result, we're going to trust the hydrogen a little bit more. So we would say that the hydrogen is each going to be +1. And in total, what does that make it? In total, that makes the overall oxidation state on all 4 carbons combined +4. That means in order to balance out the charge, the carbon is going to have to be -4. So those would be our states there. For O2, this is a bit of a trick question. We have an overall charge of 0, and we have 2 oxygens to add up to the 0. As a result, this must be 0. If you put -2 here, it was because you were thinking about them wanting the column's charge. But we cannot forget step 1. Step 1 is the absolute ruler, has no exceptions. All of the oxidation numbers added up, need to get to the charge of the overall molecule. All right, let's continue on, and let's now get into balancing redox reactions. I will tell you that most courses don't actually test this, but I'm feeling like APSC 132 this year is going to be an exception. There were quite a few practice problems, and it was, I'd say, fairly well emphasized in the lessons. So we're going to go over this. I'm going to talk about how to do this easily, and then also how to check your work, because there's a lot that goes into these. It really is ripe for any types of just like little mistakes. All right, so we're using the half reaction method here. And for the most part, I'm going to be balancing stuff in acidic solution. And in fact, even when they ask me to balance something in basic solution, I'm going to balance it in acidic solution and then convert afterward. That way you only need to learn one method, and it's just so much easier. So if you want to, you can assign oxidation numbers for this. But if you're a little bit sketchy on oxidation numbers, you don't even really need to do this for 90% of the reactions. So what realistically you're going to have to do is say, you know what? We got a lot of manganese in half of this. So let's write out our manganese version. MnO4 minus goes to Mn2 plus. And let's write out our iodine version as well. And what we need to do next is balance everything, all the atoms, except hydrogen and oxygen. Why? Because these come from water. And we're going to be adding some water and stuff later. So we balance the atoms that are not these things. So take a second and please balance those. Okay, hopefully the left one wasn't too bad. We have 2I minus going to I2. What about on the right? This one is actually even easier, but it might muck with your intuitions a little bit because it's so hard, at least for me, it's so hard not to want to balance that oxygen. So for this, it's literally going to be the exact same. So now we get to balance these, including the hydrogen and oxygen. Now that is going to be dead easy for the iodide one because it has no hydrogen and oxygen. It is already done. But how is this going to work for our manganese or our permanganate one? What are we allowed to add here? This is an aqueous solution, so we're allowed to add water. But this is a specifically acidic aqueous solution, which means we're also allowed to add H+. So we have to balance our oxygens, so I'm going to balance those by putting some water. How much water do I need on my right side in order to balance that? I have 4 oxygens on my left, so I'm going to have 4 oxygens on my right. I put a little 4 there. But now I have a new problem. Now I have a bunch of hydrogens on my right, so I'm going to need to add H2 on my left. How many H2s am I going to need there in order to make this work? I have a total of 8 hydrogens on the right, so I need a total of 8 hydrogens on the left. Each H2 gives me 2 hydrogens, so 4 times 2 is 8, and we are good. Oh, sorry, what am I saying? I'm not adding H2. Goodness me, a little bit too early in the morning for me. I'm adding H+. So with apologies, please reevaluate that. What will be our number here? It's going to be 8. Okay, we are nearly done. What we need to do now is we need to balance the charges. So I always like to balance atoms before charges. In other words, I like to balance in alphabetical order. A comes before C. Now, what can we add here? We're done balancing the atoms, so we can't add any like H+ or OH- or anything like that. The atoms are perfect. We need to leave them exactly as they are. So what can we add here? We can add electrons. So over on this left part, we have 2 negative charges. So what do we need on the right then? We're also going to need 2 negative charges. So I'm putting 2 electrons on the right side. So that was the easier of the two. Now I'm going to ask you to do the harder of the two. Please figure out the overall charges on each side and then add the appropriate number of electrons to make these charges balance. Let me know when you're done. Good luck. Okay, let's take a look. On the left side here, what do we have? We have 8 positives and 1 negative. So in total over here, we have positive 7. Okay, what about on the right? On the right, we have, I think that one's a little easier, we have positive 2. So how are we going to make these the same? We're going to have to add 2 electrons, or add 5 electrons to the left. So we're going to have 5 electrons. That's going to give us -5. And now when we add everything up, our charges nicely balance. Okay, so that's all good and dandy. But eventually we're going to have to merge these reactions together. And when we do that, we need our numbers of electrons to cancel. And I will say that being able to look at a reaction and figure out the number of electrons is so important, because that is what's going to allow you to find this Z value that we see on our equation sheet. So 3 of the 4 equations for electrochemistry have this Z value. This Z value is the moles of electrons flowing and if we're talking about this on a per mole basis, per mole reaction basis, which we normally will be, that's just going to be whatever the total number of electrons come out to be in our balanced equation. So what would the total number of electrons come out to be here? How can we balance 2 and 5? Their lowest common factor is going to be 10. So what we're going to have to do is multiply this entire reaction by 5, because we need this to get up to 10. And we need to multiply this entire reaction by what? By 2, because we need to get this up to 10. Okay, so now we rewrite our reaction. We're going to have 10 I minus going to 5 I2 plus 10 electrons. And then for the other one, we're going to have 10 electrons plus 16 H plus 2 MnO4 minus. All I'm doing is multiplying this 2 times everything. Goes 2 Mn2 plus, oh, I missed a 2 there, plus 8 waters. And I always just like to make sure afterward that I've remembered to multiply everything by the appropriate numbers, because it's so easy to lose something here. Remember how yesterday I was like, this thing is nice because once you know how to do it, you always get the right answer. This thing is nasty because even after you know how to do it, there are so many opportunities to mess up. So now we're going to add these reactions together. And hopefully it's pretty clear that the numbers of electrons are going to cancel. And in fact, they must cancel because that was the entire point of that previous step. So now we can add these things together. And I have a couple tips to help avoid careless mistakes here. Tip number 1 is whenever you're writing these reactions, try to get your arrows in the same column. Otherwise, just visually, it's so easy to mess up. Like if this entire thing were shifted over here, actually, I'm going to put it over here. It's so easy to look at this and be like, oh, the arrow is here, so we're forming permanganate. But no, we're not forming permanganate, we're using permanganate. So having your arrows line up is going to visually help you out. If you want to, bring a couple different colors of pen or pencil, and that way you can actually color code things, and that can help out as well. All right, so now all we need to do is cancel out our electrons. Well, we already did that. Any H2O or any hydroxide or H plus that appear on both sides, there's nothing to cancel here. We are good. So we actually have our completed reaction and life is amazing. That was for acidic conditions. If we turn the page, we see that we have this big blah, blah, blah about how to do it in basic conditions instead. I'm just going to walk you through this in the easiest way that I think exists, which is we did the acid. Now, well, we know if this were a base, we cannot have any H plus, right? This is a base, we can't have any H plus. So what we need to do is we need to neutralize all of the H plus. We're going to add 16OH minus to both sides. So what would it give us here? That would give us 16OH minus plus 16H plus 2 permanganate, 10 iodide, 2 manganese 2 plus, 8 water, 5 I2, and this is important. It's so easy to forget this. You got to add those 16 H pluses to, or OH minuses to both sides. So what's going to happen now? These two things are going to make 16 waters. And when you're doing these, I actually encourage you to like do them in something erasable if you can, because that way you can just make adjustments to the reaction rather than having to write it out every time. So if these are 16 waters, those are going to cancel with 8 of those. So what we're going to have then is 8 waters left on the left and no waters left on the right. So we can rewrite this thing. And we do wind up keeping our 16 OH minuses on the right. And we write out all this stuff. Lovely, lovely. This is something that, as I said, really is ripe for careless mistakes. I recommend practicing this. I'll tell you, back when I was in first year, I practiced this a ton. I actually had races with someone, and the person that I did redox reaction races with, I eventually wound up marrying. So be very careful with who you practice this with, because it is quite powerful. There's a question, what do you mean by if there's a base, then there is no H plus? All right, so when we think of acids, acids are going to form H plus in solution. And that's why we describe acids with pH, the negative log of the concentration of H plus. But if we have bases, bases form OH minus. And OH minus is not going to coexist with H plus. They're going to react immediately, like we saw up here, and form water. So we normally use something like POH for this, blah, blah, blah. But the point is, OH minus only allowed in basic solution in any kind of appreciable amounts. H plus is only allowed in acidic solution in any appreciable amounts. And water is allowed in both. All right. We are now going to do some practice. So let's first do one that's not too mean. Let's do our kinetic study or our electrochem study problem. Question 12. Give this a go. Good luck. I'm going to start putting a big ol' hint up here. I'm going to write out the half reactions. If you're having trouble with this, see if the half reactions help and see if you can continue on. Okay, the first one is up there and balanced. See if you can use that idea to finish the second half reaction. All right, we now have all of our atoms balanced. So next we're going to need to balance our electrons. So think about the charges present on both sides of both of our half reactions and balance the electrons for both. Oops, yes. There's a question. Did you switch these by accident? Yes, I totally did. Went to all the trouble of saying there were 6 oxygens on the right, therefore we need to add 2 oxygens on the left. And then I completely did the opposite. That's much better. So again, what I just did was I took the two waters that were on the right of the first reaction, put them on the left, and now we have the H pluses on the right. Sorry about that. All right, so let's balance all of our charges then. So on the left of the first reaction, we now have -2 after that switch. And on the right, we now have +2. On the far right reaction, we have +3 on the left. And on the right, we have a big ol' 0. Okay, lovely. So now what we're going to do is we're going to have to add 4 electrons on the right of the first reaction. Lovely, lovely. And for the one on the right, the second reaction, we're going to have to add 3 electrons to the left side. Okay. Looking good. But now we're going to need to make these things balance. So we're going to need to add these together in a way that will make it so that the electrons balance. Okay, great. So we're going to need to multiply this one on the left. Ooh, it's a little nasty. By 3, this one by 4. Okay, so we do that then. We're going to have 6 waters plus 3 C2O4 2 minus going to 3 CO3 2 minus plus 12 H plus 12 electrons. And then for the one on the right, take a sec, write that out. Okay. So on the right, well, actually, just before that, there was a question about up here. Ooh, I did not fix my charges properly, did I? The charge on the right side should have been -4 plus +4. It should have been 0. Ah, As I said, these things have lots and lots of opportunities to get them wrong. So as a result, instead of adding 4 electrons, I'm going to be adding 2 electrons on the right. That's going to change this too. My apologies here. So what are we going to have to multiply these by then? 3 and 2. Because we want the amount to be 6 here. And this is somewhat good practice of actually going back and fixing things. So how is this going to affect this? How is that change going to affect this? Well, instead of multiplying by 6, we're now multiplying by 3. So this is going to become as written here. Okay, lovely. Then multiplying the right side, or the second reaction, by 2, we're going to get, oops, get that out of there, 6 electrons. Okay, yeah, the other stuff looks good. Good. So we're going to have 6 electrons plus 8 H pluses plus 2 MnO4 minus, arrow, 2 MnO2 plus 2, nope, plus 4 H2O. And at this point, I always just like to check to make sure that all my charges are making sense here, my charges are balanced, because this is, we're nearing the end and we've already had lots of opportunities to make mistakes. So on the left side here, what is my overall charge? Going to be 3 times 2, it's going to be -6. As usual, I'm going to give you the hard one. What's my overall charge on the right? My overall charge on the right is going to be, and I'm going to show this explicitly, 3 times -2 plus, just -2, great, plus 12 plus -6. And this is totaling to be 0. So that tells us that there is a problem here. So what is the problem here? Can you spot it? So you only need to pay attention to the charge species. So let's just make sure the charge species all make sense. We went from here to here. We didn't have to make any changes with that charge. That was just balancing the hydrogens and oxygens. We went from here to here. Whoa, something happened from here to here. We dropped that 2. So we'd better put in that 2. And then when we multiply that by 2, it's going to come out with a 6 here. That is why it is so, so important to be able to check these things, because you will almost inevitably make mistakes the first time you go through this, even like the first 5 times you go through this. How does that change our equation? We now have 6 times -2. So now all of this does total to -6. And as a result, we can have confidence that we have this one right. Please take a sec, check the charges on the second reaction, make sure everything's good. Okay. On the left, we have -6 plus 8 minus 2. So in total, that is 0. And on the right, we have 0. Fantastic. Oh my goodness, friends, we are nearly done this terrible, terrible question. This would, of course, not be a multiple choice on your exam for multiple reasons. So now we can add these two things up. All right, so we're adding things up. Do we want to cancel some stuff first? I think we should. On the left, we can cancel out the 4 OHs, or the 4 waters. And this is going to become a 2. We can cancel out some hydroniums. We're going to have 0 hydronium or 0 H plus on the left and 4 remaining on the right. As a result, we're going to have, well, really, we're going to have the end of the question because we can finish it at that point. But let's imagine that they asked us to balance this whole thing. Note that I'm also leaving off the electrons because they are, of course, going to cancel. On the right then, we have 6CO3 2 minus, 4 H pluses left. And then 2 MnO2. Fantastic. I always just like to make sure what should be on the right side there. Those things, great, they all match. All right. But they asked us to do this in base. So what do we do? See if you can wrap up this question. You can do it. Good luck. All right, in base, what are we doing? We need to get rid of all of the H plus. As a result, we're going to be adding 4 hydroxides on the right, 4 hydroxides on the left. So what's that going to do? Importantly, it's going to turn these into 4 H2Os. Do you remember what this question is actually asking? It's asking for the coefficient on the water. So if we have 4 H2Os on the right, that's going to cancel on the left. We're going to wind up with 2 H2Os on the right. And 2 is going to be our final answer for this mega question. A is the best answer for 12. Okay, so that was a lot. I'm not going to put you through these again, but I am going to give you a number of different problems to practice because you will very likely be seeing this kind of thing. So you can practice this one. You can also practice your electrochem. Actually, let me just give you a page number. That'll be easier. Your electrochem knowledge development questions for these two. So page 21, question 1. Page 21, question 1 of the supplement. And once you've done like probably about 5 of them. Normally takes about five entire practice things to become quick and confident in it. Then you should be pretty good. If you want more practice, the 2019 exam, part 3, question 4 is another one like this. So hopefully that gives you plenty. And if you are, if you've done all of these and you still need more practice, just I guess email me and I'll make some more questions for you. But my guess is that'll be enough. All right, we are now looking at electrochemical cells. Woo! Electrochemical cells are going to do a few things. They're going to transmit electrons from one side to another. And they're going to do this with a fair amount of force, not like literal, like mass times acceleration force, but they're going to be trying to push these electrons. And the force of pushing electrons is known as voltage. So whenever we're talking about how much reaction wants to go, there are a few different ways that we can do it, but in this particular situation, we're going to use E, or our potential, as this proxy. And there are a number of other ones that we've seen before. We've seen K is also an example of how much the reaction wants to go. We've also seen delta G is another way of expressing how much the reaction wants to go. For delta G, if it's negative, the reaction wants to go. For K, if the number is greater than 1, it wants to go. And for E, if it's greater than 0, it wants to go. So then it should make sense that these things are all going to kind of be intertwined. You should be able to relate them. And when we look at our equation sheet, lo and behold, we can relate E and Q. We can relate E and delta G. We can relate E naught and K. So all of these things are indeed interconnected, and very likely on the exam, you'll be asked to convert from one to the other. For the most part, these questions tend to be pretty straightforward. The tricky parts are normally figuring out the E naught of the cell. So this is the E under standard conditions. Remember what that standard conditions means? It means 1 molar and 1 atmosphere of any gases. And if we don't have the naught sign, that means any circumstances. And I'll talk more about the Nernst equation and these particular things in a little bit. For now, I just want to give you kind of a big picture here. Very often you'll be asked specifically about either the anode or the cathode. The anode is always going to be where oxidation is occurring. The cathode is always going to be where reduction is occurring. You remember oxidation and reduction from yesterday? Oxidation is going to increase the oxidation number, and reduction is going to reduce the oxidation number. So we can remember that the anode is the site of oxidation by thinking of an ox. And we can remember that the cathode is the site of reduction by thinking of this red cat. All right. So let's focus for now on galvanic cells. Galvanic cells are what we're going to see, I don't know, probably 70% of the time on the exam, because they're the ones that are actually obviously useful to us. Galvanic cells have a spontaneous redox reaction. What that means, what does that mean in terms of delta G? What's delta G? means delta G is negative, and the reaction wants to go. Ooh, excuse me. As a result, this reaction wants to go, and it's going to try to push its electrons to actually go. So it's going to give us both energy and current. The anode is negative, the cathode is positive. This is something that I think is unlikely to come up, so I'm not going to dwell on this and why it switches with electrolytic cells. But you can feel free to ask in the Q&A after class if you are curious about why that is. But the first two are definitely the main two here. So if the reaction wants to go, why isn't it? The idea here is that it's not going to go right away because we actually have the two reactions in separate situations. So what that means is that we've got one half reaction stuck over here and one half reaction stuck over here, and we can throw a big old resistor in between them to make it difficult for the electrons to move through. So we have copper and we have copper 2+. How can we arrange those species to make it either an oxidation or a reduction reaction? We're told this is our anode, so which should it be? Oxidation or reduction? An-ox, so this is going to be oxidation. So how would you write out an oxidation reaction between copper and copper 2+? Give that a try. Okay. So we need the oxidation number to increase if it's oxidation. The oxidation number of copper is 0. The oxidation number of copper 2+ is 2+. So the oxidation reaction would look like so. Then we need to balance the charges. So where would we put some electrons here? We'd put electrons on the right side to make both sides 0. And now very often we're going to be able to figure this out like we just did, but we're also going to be able to check it using our equation sheet. So if we look at our equation sheet, I'm going to rotate this again. We have a big set of standard reduction potentials. So we could look through this and try to find copper. And where do we see copper here? We see some copper here. Is there any other place that we see copper? I don't. I'm actually kind of surprised by that. They'd normally include copper 2+ on this, but whatever. So we can just make sure that our reaction actually lines up with something that makes sense. And life's good. What about for the right side? We're going to do this a little bit faster. Take 30 seconds and write out the reaction that's going to be happening on the right side. And I'll let you know that the silver here is silver plus. Okay. So to reduce this oxidation state, we're going to have silver plus. It's going to silver solid, so from +1 to 0. And as a result, it needs an electron on the left. Lovely, lovely. Now, we couldn't just mix these right away. We'd have to multiply the one over here by 2 to make it so both sides have 2 electrons. But we don't need to care about that right now. We can just make sure that this makes some sense. Silver plus going to silver. So we'd look at here, and do we find any silver? We do. And we see silver plus going to silver. It eats up 1 electron, so it makes perfect sense. We probably have the right answer, and we do. All right, one other thing is that when sometimes they're going to ask you about the direction of electrons. And the direction of electrons is going to be from the place that's providing them, from the place that's making them, to the place that's consuming them. Hopefully this makes some sense. Just like food grows on a farm, it's produced on a farm, and then it's sent to the grocery store and eventually sent to our house and our mouths. Goes from where things are created to where things are consumed. Now, a little bit weird thing, if you look in your textbook or if you look in other external sources, you're going to see that current flows in the opposite side of electrons. However, based off of the solutions to the knowledge development questions, when this course says current, it doesn't mean conventional current. It means electron current. So it just means the direction of electron flow. So we are going to scribble that out. But I wanted to bring that up just because if you look in other sources, you're going to see things that go against what you see on your solutions of the knowledge development questions. And I didn't want you to be wondering why. All right. Let's now zoom in on this galvanic cell. On the left, we have zinc solid being turned into zinc 2+, lovely, lovely. And it is producing electrons. Great. So the electrons are going to be leaving here, and they're going to be whoop, 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 going over there. And they're going to be consumed by this copper 2+, turning this into copper solid. So what would happen to these two electrodes, the metal things here? As time progresses, what's going to happen to this zinc? Is it going to get bigger, smaller, or stay the same? It's going to get smaller because it's being used up, right? So it eats away at this electrode. And then the copper electrode is going to get bigger. It's going to kind of like grow a beard. And that's that. But now, if over here we're losing negative, and over here we are gaining negative, wouldn't that mean that eventually we generate a positive charge on the left and a negative charge on the right, and eventually our beakers are going to attract each other coulombically, smashing together, ruining our experiment and our entire day? Well, that's not going to happen because we have this lovely thing called a salt bridge. And a salt bridge is going to have, usually, inert ions. And inert just means they're not going to react. So inert just means they're not going to react. And their entire job is to make it so that these things get to cancel each other out. And these things get to cancel each other out. And there's going to be no net charge in either of your positions there. All right. So let's continue now. And briefly, we're going to look at electrolytic cells. I say briefly because there are only really two different ways that they're going to tend to test you on electrolytic cells. And they tend to be very mathy, not very philosophical. So we're just going to see those types of questions. We're going to ace them, and then we're going to move on. For electrolytic cells, you need to provide some kind of external potential, because electrolytic cells are not going to react just by themselves. They are non-spontaneous. And what that also means is that you don't even need to separate them, because if they're not going to react by themselves, no need to keep them separated. So what we can do is we can pump some current through this thing, and that can allow us to get to a reaction that would otherwise be very non-spontaneous. So having sodium chloride actually be electrolyzed to chlorine gas and sodium plus, or yeah, to sodium metal, that's going to be hard to do because we've seen sodium chloride everywhere, right? It's really, really stable. And chlorine gas and sodium metal is considerably less stable. And in a few minutes, we'll see how we're going to be able to predict that in more detail. All right, so we have our summary here. And the last thing that I want to bring up is this idea of Faraday's constant. So Faraday's constant is 96485 coulombs per mole of electrons. We have that on our equation sheet. That is great. However, they're not that useful in helping us out with the relevant equations for Faraday's constant. So we have this, and we have this, and we have this, but you might be asked another type of question about electrolysis. And this other type of question involves stuff like letting the cell run for a little while, and then saying like, well, how much reactant reacted? And in order to do that, we need to know two equations. The first one is I'd say much easier. If they tell us that Faraday's constant is 96485 coulombs per mole of electrons, how can we find Faraday's constant? Well, we can think about the units. So Faraday's constant is going to be equal to what's measured in coulombs? Charge. And what's measured in moles? Moles! So that is one of our very useful equations. Another useful equation is what I call the quit equation, for obvious reasons. So we have the current, or excuse me, the charge, and that's equal to the current at the time. We'll see some examples of these in probably an hour or two. But these equations are going to be very useful to us. Okay. Now we're running a little bit early. I'm going to call a break here. It's a natural stopping point, so please walk around a little bit, take 10, let your brain recharge, and come back then. All right, friends, we are back. When we last left our heroes, they had seen all of these lovely differences and similarities between galvanic and voltaic and electrolytic cells. So now what we're going to do is I'm actually going to show you a little addition. So this is not in your book. I have added this, and this will be posted. And this is what's known as the shorthand cell notation. This is usually how it works, but I have actually seen times where your instructors have not followed this convention. So they tend to use something that's a little bit less predictable. Usually, you have your anode reactant and anode product, then you have your salt bridge, and then your cathode reactant cathode product. Now, the deviation that I've seen is sometimes they don't actually list these in terms of reactant product. Normally, you would, but they just write like cathode stuff. And what I mean by that is they're writing the species in no particular order. They don't actually normally mix up with the anodes, but something that we do want to be ready for. So how do we figure out what's going to be a reactant and what's going to be the product then? Well, we know the anode is going to be the site of oxidation. The cathode is the site of reduction. So if they just give us the stuff, we can still figure out what is what. Let me give you an example, and then we're going to do a couple practice problems. The examples here. We have the stuff going on at the anode. That is where the zinc and zinc 2+ is. So that's going to be listed there. The stuff going on in the cathode is going to be listed there. Now, this vertical bar represents a change in phase. Oftentimes, through a reaction, you are going to have a change in state, like we do here from solid to aqueous, from aqueous to solid, but not always. And in fact, one of the very favorite half reactions in this entire course is the further oxidation of iron 2+. So we have a reaction of iron 2+ going to iron 3+. They are in the same state. They're both aqueous. And as a result, we can't put a line between them, so we just put a little comma. And that's good enough for us. Excuse me. Now let's take a look at this review question here. Give it a go. Try to turn this into a reaction and see where that gets you. Good luck. All right, I'm going to interrupt here. On the left side, we have our anode. So this must be the site of oxidation. Between zinc solid and zinc 2+, Which one has the higher oxidation number? Zinc 2+. So that must be the thing that we are forming if we're oxidizing. Now, what about copper? Over here, this is the site of reduction. And as a result, we must be going from copper 2+ to copper solid. And the stoich is all one across the board here. That isn't always going to be the case, but it so happened to be the case because both of these had a difference in charge of 2, so life is really good. See if you can use that information to wrap up this question. Let me know what you pick in the polls. Good luck. All right, let's wrap this one up. Seeing mostly C and D here with a little bit of A, they tell us that 0.1 mole of copper is formed. 0.1 mole of copper is formed. Well, based on our stoich, that must mean how much zinc was consumed? 0.1 moles, because it's a 1-to-1 ratio. That's how much was consumed. But let's look at the units here. They're not asking for this in moles, they're asking for this in grams. So A is going to be out. So converting moles to mass, we're going to multiply by the molar mass. Where's my sheet here? There it is. So for, what is this? Zinc. For zinc, it's 65.4 as our molar mass. So that comes out to be 6.5 grams. And C is our best answer here. Question 7 is similar, but considerably more tricky. There are a few twists to this one. So give this a read, give this a go, and I'll interrupt a couple times with some hints. Good luck. All right, I've got my first interruption here. They tell us we have this copper nickel cell. I guess that should be copper silver cell with these things. And this is reacting spontaneously until the copper electrode reached this. So the copper electrode is being used up, and therefore copper solid must be a reactant. So we must be using copper solid to form copper 2+. They ask us for the final mass of the silver electrode. So we're looking for the final mass of that. Now, we could write this out, but hopefully this reaction is making some of you uncomfortable here, because it cannot be right. This cannot be our balanced reaction. How do we know this? Well, over here, we have a charge of +1, and over here, we have a charge of +2. So what are we going to have to do? We're going to have to multiply both of these silvers by 2. Then our charges are going to balance, and then life is good. See if you can use that information to finish up this question. Best of luck. But a few more hints up here, a little bit of a roadmap. I'll tell you that someone who recently selected got almost all the way there. But if you just put in an answer, check out those last couple steps, and that might allow you to revise your answer here. You have 2 minutes remaining. Keep fighting. Oh, we just got our first correct answer. Congrats. Anyway, minute and a half left. Enjoy. All right, I'm actually going to call this a little bit early because most people have their answers in. Seeing largely D with some A as well. Those are two good answers. And between the two, D is our better answer. So we know how many moles of copper we have, or how many moles of copper we used. So then, how many moles of silver did we gain? Well, we have a 2-to-1 ratio there. So that is going to be 0.02 moles. Okay, so what's our mass of the silver gained then? It's going to be 0.2 times the mole mass of silver, which is 107. So we're going to come out with 2.14 grams. But that is not what the question is asking for. They're not asking you for how much silver was gained. They're asking you for the final mass of the silver electrode. It started as 3 grams. So if it's gained 2.14, we got to add those two things up. And we come out with 5.14 grams. And D is our best answer for this. All right, lovely, lovely. Bit of a tough question, but the questions that they've been asking you for this kind of thing have tended to be pretty tough. So now let's continue on and get to, I'm so sorry, get to a topic with a lot of potential. I hope you are absolutely charged to be learning about this very current field. All right, our potentials are roughly how much a reaction wants to go. Based on those jokes, you can probably tell that I became a dad relatively recently. So this kind of thing just like flows out of me at this point. We are going to be provided with a standard redox potential chart. So that's all good and fun. In the middle, there is our standard hydrogen electrode. We don't actually care about that much for this course. I mean, it's given to us. It was important in the construction of this, but other than that, it's actually not very testable in a lot of ways. So how do we use this kind of thing? All of these are half reactions. So that means if we've got an overall reaction, we're going to have to put our half reactions together, right? But it's called redox. You need reduction oxidation. You can't have re-re. So what that means is you're going to have to take one of these and you're going to have to flip it. And when you do, you're going to be flipping the sign of the potential. The way that this is expressed on our formula sheet is shown right here. If we want to find the overall cell potential, you flip the anode, because that is your oxidation. Flip the sign of that to make it negative, and then you just add the two up. If you get a positive E naught, then we'd say that the reaction is spontaneous at standard conditions. So let's turn the page here. And we have a beautiful picture of the standard hydrogen electrode. Under standard conditions, what do we have? We have 1 atmosphere of H2 gas. We have 1 molar of H+. Because remember, at standard conditions, everything is 1. But in order to make a cell work, you need some kind of metal to conduct electrons. So the metal used for a standard hydrogen electrode, and in fact used for pretty much all of our electrodes where we don't have a solid here, is going to be platinum. So very often in your half cell or in your shorthand cell notation, you're going to see like platinum on the side. The platinum is not a part of the reaction. It's just allowing the reaction to work. It's acting as a catalyst. So great. Let's look at this and ask ourselves, is this cell at standard conditions? I want you to try to figure that out in 2 different ways. Good luck. Okay, so way number 1, and I think this is the easier one, is all of our concentrations are equal to 1 molar, and all of our pressures are equal, I'll say partial pressures. So there's only 1 here. All of our partial pressures are equal to 1 atmosphere. So that's one way we know this thing is at standard conditions. Can you think of another way? I'll give you a little hint here. Got 30 seconds to think of it. Good luck. Another way would be to check this. We could find our E naught of the reaction based off of the E naught of the reduction minus the E naught of the oxidation. And when we do that, we'd find that this is exactly 0.337. But now let's look at some like full examples, because I don't want to just leave you with that. I will say this equation in the box here represents after flipping the oxidation sign. And depending on where you look, you're going to see either a plus or a negative here. If you see a plus, it's because they've flipped the oxidation sign already. If you see a negative, it means they haven't flipped it. So what I mean by that is if we have E naught of the anode, this is actually like smuggling in a kind of interesting and complicated idea, which is the idea that this E naught is the reduction potential for an oxidation reaction. So again, a bit of a weird idea, and that's why, depending on who you ask, that's going to be a positive or a negative. But the point is, you're going to have to flip something. And when you flip it, you're going to want to flip the sign and add them up. Let's drive that home with a couple ideas here, with a couple examples here. I'll help you with the first one. So here, what do we need to do? To make this overall reaction, we're going to need to flip this. And we're going to need to keep this bottom one. Now, how do we know that? Do we just always flip the negative one? Do we just always flip the lower one? No. That is only going to work if you have a galvanic cell, and they will try to fool you on this. So how do you know which one you're going to flip? You're going to say, which reactants do I have? Which reactants do I have? So what do we have? We have sodium, solid. So this needs to be on the reactant side, and that's why we need to flip this reaction. What else do we have? Chlorine. Chlorine is already on the reactant side, so we're going to have to keep that. So the way that I like to think of this is when you flip the reaction, you flip the sign, and you just add the two up. 4.07 volts. D is our best answer there. I'd like you now to please try this next question. Good luck. All right, let's take a look here. Seeing a fair bit of B and C. So the difference here is, did we flip, well, C would flip both of them? That doesn't make a lot of sense, because if we flipped both of them, then we'd have the electrons both on the same side. So that doesn't make a lot of sense. We need to only flip one of them. That's both because we need a reduction and an oxidation reaction, but also because we are going to need to keep the gold 3+ on the left, and we're going to need to get the copper 2+ on the right. So we're going to need to flip that. So we flip that, we add the two up, and we get 1.16 volts. B is our best answer. You always want to think about what reactants you have. Okay. Let's now take a look at 2019, question 13. Actually, we're going to do that one later. Changed my mind. Let's instead do our development question 2. So we're on page 22 here. Give this a go. Just in case you do not have your formula sheet handy, I'm going to paste the SRP table on here as well. Unfortunately, the picture that they've given us is a little bit pixelated, but hopefully it is still somewhat legible. Good luck. Dropping in for a couple hints here. They kind of mask what we're looking for. They say we're looking for potassium permanganate, but if we look around here, we're not going to find any potassium permanganate. Instead, what we're going to find is just the permanganate. And same thing with our iron sulfate. We're not going to find any iron sulfate on this, but we will find iron 2+. And we know it must be 2+, they said iron 2 sulfate. So these are our potential reactants. See if you can find those equations and then use that to make our balanced redox equation. Keep fighting. Show me when you're done. Good luck. All right, I'm popping up to show a common mistake here. It might be tempting to be like, oh, iron plus, okay, we're going to add a couple electrons to that and give us this. However, what would be the problem here? The problem is that we have electrons on the same side for both. Okay, can we flip this? If we flip this, then we have a new problem. We have no iron solid as a potential reactant. So what that tells us is that this cannot be our reaction. Do you spot any other places where you can have iron 2+? There's another place, and that is here. So if we were to write that one out, we'd have this. And is this what we're looking for? Not exactly. We need iron 2+ on the reactant side. So what that means is we're going to have to flip this. Can we flip this? Do we have iron 2+ on the reactants as a potential reactant? We absolutely do. So we can flip it. And when we do that, we're going to want to flip that E0. When we flip that E0, it becomes negative. And now we are off to the races. There's a question in the Q&A. How do we know which permanganate to use? So permanganate is going to be Mn O4-. So we just kind of scan through. Where do we have that? We have it here. A lot of people would want to use this one here, but this is not quite the same. This is MnO2 solid. So we can't be using that one. We can keep on scanning, and I don't actually see any other manganates. We can look in our basic solution, but they told us that this thing is acidified. So we just really have the single option here. All right, please try to wrap this up. You've got 60 seconds. You've got a minute and a half left. Good luck. All right, let's wrap this up. So we're going to add these two things together to get a balanced redox reaction. Ooh, but we're going to have to multiply this whole thing by 3 to make it so that the electrons cancel. All right, so I'm writing this out, and I'm going to do it a little bit squished, because otherwise I will totally run out of space here. And then, got to make sure I multiply that by 3. So easy to forget. You ever wonder if you're the only person who makes a mistake all the time? And when you're teaching something, you keep being like, oh, this is so easy to forget. And everybody's just like rolling their eyes and be like, no, Mike, that's only you. All right. Oh, and I dropped a 2 there. Great. So this is going to be our overall reaction. And there was a question in the Q&A before about like, why don't we need to bother like multiplying any of these things when we multiply the reaction by 3? It's just because potential is an intensive property, so it's not going to depend on the amount. So you can multiply the reaction by 3 and not have to do anything with the E. So what does our E0 of reaction come out to be? our E naught reaction, we add those two things up, and we get something that is pretty darn positive. We get 0.929 volts. And what does that tell us about the spontaneity? Is the reaction spontaneous or not? E naught of reaction is positive, and therefore the reaction wants to go. It's spontaneous. Yay! And just a quick note that if you look at the instructor solutions to this, it's fairly different, and it's fairly different because they decided to use a reduction potential that was not given to you. So kind of annoying, but so this would be the correct answer given what we are actually given here. All right, let's hop on back. We're on page 50 here. This is a really useful idea that is very likely to come up on your exam. In fact, there's a real banger of a question that we're going to do later that revolves around this. So if we have electrolytic cells, there are often the obvious things. So they say, like, actually, I'll just show you the type of question you'll be seeing with this. So this looks so simple, right? It's an electrolytic cell, and they tell you that you have lithium and bromine. It's LiBr, so it's lithium plus and bromide. And it's like, okay, great. I can work with that, right? I'll just find my lithium plus, and I'll just find my bromine or bromide, and I'm off to the races. However, we got problems here. The problem is that you don't just have lithium plus and bromide. You also have other stuff. Specifically, they tell you that this is a 1 molar lithium bromide solution, which means you also have water. So they are actually quite nice, and they box a couple water reactions for you. The water reactions that we're looking at, one of them is this. So that's great. And do we want to talk about this whole thing right now? No, we're gonna keep talking in theory, and then we'll get back to this question soon. So if you want to predict these products, what you want to do is you want to write out all of the oxidation all of the ones that could happen with our oxidation, all of the ones that could happen with our reduction, and then at standard conditions, you just pick the highest E naught or the least negative, another way of saying that, E naught, and you're good. So, all right, let's see what this looks like in this one. So what are our possible reactions? Take a second and list them all out here. Okay. So we could have our lithium reaction here. Lithium plus an electron goes to and returns from lithium solid. And that has a very, very low potential, 3.05. So that is going to be really, really difficult to do. Is this oxidation or reduction? This is reduction. And as a result, I write it in red. For bromide, what could we do there? Well, we would need to flip this reaction. So it would be 2 bromides going to and returning from bromine liquid and 2 electrons. And its E naught would be, we're going to have to flip it, so negative 1.065. Our water, well, they're nice enough to give us one of those, and they box it quite nicely. So it's going to be 2H2O making oxygen gas, and oh, I lost it. Come back there. There it is. Plus 4 electrons. And is this oxidation or reduction? If you're having trouble thinking about it, because like the oxidation numbers are harder to spot here, one thing that you can do is say, well, up here, was this oxidation or reduction? This was oxidation. And how do we know that? Because the oxidation state went up. Another way of identifying oxidation is that it spits out electrons. So this thing is also spitting out electrons, and as a result, it is oxidation. Okay, do we have a potential reduction reaction for water? We do. We look down here, and let's see. Down here we have oxygen gas mixing with water, and they didn't tell us that we have any oxygen gas handy, so we probably shouldn't be using that one. At the very bottom, we have this one, 2H2O plus 2 electrons goes to and returns from H2 gas and 2OH minus. And please take a sec, figure out, is that oxidation or reduction? It is consuming electrons, so it is reduction. And oops, I was a little bit lazy writing out my E naughts, so I'm going to write out my E naughts here. First E naught is it 1.229? Not quite. I flipped the reaction, so it's going to be negative 1.229. What about this other one? Is it negative 0.828? Yes, that's exactly what it is. I did not flip that one, so it's going to stay as negative 0.828. Okay. So now, under standard conditions, which would react? Remember, you need one oxidation reaction and one reduction reaction. Try to figure that out based on what's written up here. All right, I'm going to interrupt and do the first one, oxidation. Remember that your goal is to choose the biggest E naught. And oftentimes for electrolysis, that's going to mean the least negative E naught. So if we're looking at our oxidation reactions, we just choose the least negative E naught. So that would be our bromide one. What would it be for the reduction? You got 30 seconds. All right, looking strong. Fantastic. We're comparing the two possible reductions. You just pick the least negative one. That is going to be H2O. All right, so if the question were asking about standard conditions, those would be our answers, or I guess these are our reactants. So the products would be the other things. Br2 and our reduction one, H2 and OH minus. This would be under standard conditions. We will come back to this question because it is not technically asking us about standard conditions. So more on that soon, something to look forward to. Let's now pop back here. And if we want to convert between E and G, we use this equation. The N here, again, is the moles of electrons flowing. So it is your balanced number of electrons. Balanced stoichiometric coefficient on the electrons. That'll allow you to cancel things out. So let's see one example of that. We're going to go to 2019 question 14 on page 40. Good luck. Your first hints are up there. You've got 1.5 minutes remaining. All right, let's wrap this up. Seeing mostly seeing mostly C here, C is not our correct answer. You picked C, you probably dropped that negative. I like to do these qualitatively first. So once I know that my E naught is positive, I know my reaction wants to go. And therefore, my delta G naught is going to be negative. And that allows me to cross out B and C right away. Of course, not useful on a long answer, but when you get to the end and you write down your answer, you want to make sure that it does abide by your qualitative reasoning. All right, so we found our E naught of the reaction. We had to flip this second half reaction. And when we did that, we came out with 3.156 volts. So we want to use this equation. And of course, the trickiest part of this equation is figuring out what this N value is. We said before that the N value is the number of electrons in a balanced equation. So how do we balance these equations? We're going to have to multiply this one by 2. And when you do that, you're going to get 2 electrons here, 2 electrons here. So the number of electrons that we're canceling is going to be 2. I think on our equation sheet, they write that as Z, but it's the exact same type of thing here. So I'll just write it as Z instead to make things match. And then after that, we just plug in our numbers and life is good. -2 times 96485 times 3.156. And we come out with a huge number. I'm going to put it in kilojoules because they asked me to. 609 kilojoules per mole. We have another of the same question here. When we multiply by 2 here, why don't we have to multiply the E value? We don't have to do that because potential is an intensive variable. Does not depend on the extent. It's not like enthalpy. If you're thinking like Hess's law right now, where you have to multiply this by 2 as well, enthalpy is extensive, depends on the amount, and potential is intensive, does not depend on the amount, so we don't have to multiply that by 2. All right, let's pop back into our booklet now. And I think we're probably good for this, so we're going to skip this one. And we get to our lovely Faraday's laws. So for this, we have this kind of blah, blah, blah. I don't think we need to care about this. But this is a useful equation. It's not an equation you need to memorize if you already know Q equals IT, and Faraday's is Q over moles of electrons. Because you can make this out of these two things, but so I recommend remembering these. For reasons we talked about before, QUIT is nice and easy to remember, and the units of Faraday's constant give you charge over moles of electrons. Let's make sure. Coulombs per mole, charge over moles. So using that, I want you to try rapid review question 9, and I'll just remind you of the units of current are coulombs per second. Seconds matters here. Good luck. All right, let's talk this one through. They're telling us that we have silver plus, and it's being deposited, so it's turning into a solid. That tells us the reaction must look like this. We have an equation to find out the moles of electrons. So let's do that. We have a current of 15 amps times a time of, it's in minutes, we got to make sure we convert that into seconds. That's going to be 600 seconds. All right. Our Faraday's law is, or our Faraday's constant is 96485. And we're going to come out with, this is multiple choice, so I'm just going to be really approximate here, 9 times 10 to the negative 2 moles. This is moles of electrons, but what is the molar ratio between electrons and silver? It's 1 to 1. So what that means is that we also have a moles of silver of 9 times 10 to the negative 2 moles, and then converting to mass. They give us our molar mass, which is so kind of them. And we come out with about 10. So A is our best answer here. That's about the level of difficulty I'd be expecting here. Maybe they would make this not a 1-to-1 ratio, so then you'd have to multiply. But that's about as hard as this one I expect is going to get. If you are feeling super confident and you want to prepare for the absolute worst case scenario, then you can try review question 10. But I think this one is a bit too hard, a bit harder than, not too hard, but a bit harder than what you're likely to see on your exam. So we're going to skip over that. This section, we have this kind of like blah, blah, blah derivation. And the idea is that we can make this equation. But we're given that equation, or we're given a different version of that equation. So I'm not going to talk about the derivation. It tends to be relatively straightforward how to apply this. The two tricky parts, as usual, are figuring out the number of moles of electrons that are going to cancel. That's why the balancing section was so important and why we spent so much time on it. And finding our standard potential. All right, so we are going to continue now and get to the Nernst equation. It's been a while since I've thrown a star down on this, but this is super, super important. Guaranteed you will be seeing this on your exam. The idea of the Nernst equation is that we're not always going to be doing things under standard conditions. So what we need is we need to take our reference, our standard conditions, and do an adjustment. And this kind of equation is just so popular in chemistry. I mean, in thermodynamics, we saw this one. The delta G is equal to the delta G under standard conditions plus this. When we saw the Henderson-Hasselbalch equation, we saw the same type of thing. Our acid over our base. Oops, use consistent. So we had the reference and then the adjustment. The reference and the adjustment. So very common. So let's just try to get some kind of intuitive understanding of how this is going to work. Let's imagine we are looking at this reaction, our zinc-iron reaction. Let's not think quantitatively right now. Let's just think with like Le Chatelier's principle. So if we had an initial cell value of 0 volts, not a standard cell potential, not a standard cell potential, an actual measured cell potential, what's that telling us? Well, if E equals 0, does the reaction want to go? No. Does it want to go in the reverse direction? No, actually, it's quite happy the way it is. It is at equilibrium. Amazing. What would happen to the E cell if we added some iron 2+? Based on the Chatelier's principle, if we add some iron 2+, it's going to shift the reaction to the right. So does the reaction want to go now? It does want to go, and therefore E would become positive. All right. What happens if some iron 2+ was removed? I'm not going to belabor this point. I think you probably get the idea. It's going to shift the reaction to the left. So the E is now going to be negative. And another way of saying that is it's going to be spontaneous in the opposite direction. Spontaneous in the opposite direction. Okay, so hopefully that's building our intuitions a little bit. It agrees with Le Chatelier's principle. How does it affect things? It affects things because that Q is the ratio of our reactants and products. Just a little reminder here, we're going to have products over reactants. And we might have some exponents there if the stoichiometric coefficients are not all 1 to 1 to 1 to 1 to 1. So let's see this exact situation in a way that they would ask us on the exam. So we've got a lovely 3-parter here. Please start out with part A. Good luck. All right, let's go through this. We're looking for the overall potential for this thing, and it is definitely not at standard conditions. So we want to use our Nernst equation. And what is our E naught going to be? Well, what do we need to flip here? We need to be using zinc, so we're going to need to flip that. And we need to be using iron 2 plus. That's going to stay exactly as is. So when we add up those two, we come out with 0.32 volts. Now we can use this equation, 0.32 volts minus our 8.314 times T, wow, really precise room temperature here, 298.15. What is our N value here? Or Z value, same thing. Well, how many electrons must be flowing in this? We've got them already balanced nicely for us, so it's going to be 2. And our Faraday's constant, 96485. And then we get ln of Q. So we need to know which ones are going to be our reactants and which ones are going to be our products. Now, thankfully, they gave us our overall reaction here, which is very kind of them. So we know that zinc 2 plus is going to be our product. And iron 2 plus is going to be our reactant. So when we sub those numbers in for our ln, zinc 2 plus is 1.9 molar. I'm not going to bother with units here. Iron 2 plus is 0.1 molar. Do we need any exponents here? We don't because everything is 1 to 1 to 1. But if it weren't 1 to 1 to 1, we'd have to put those as exponents. And when we crunch that all out, we come out with 0.282 volts. Now, does this make sense? This is a question that you always want to ask yourself after you come out with a value. Does this make sense? Should this number be lower than if everything were at standard conditions, if everything were at 1 molar? So what do we have more of? We have not as much of our reactant. We have more of our product. As a result, yeah, this battery is getting kind of tired. It is losing its reactants. It's almost gone. So we should expect it to be pushing forward a little bit less than it used to be. As a result, we should expect our E to be a little bit less than our E naught. All right. That kind of thing is going to be so important, like guaranteed you're going to see a question very much like this. Let's let this sink in. And you are putting in work here, so treat yourself. Grab some tea, some hot chocolate. Please come back in 10. I'll talk to you then. All right, friends, we are back. When we last left our heroes, we saw the very, very important Nernst equation, and we used it for our first time, at least in this session. So what I'd like you to do is please now try answer B and C here. Good luck. Okay, I'm not going to belabor this one because I think this one is more straightforward than some of the other stuff we're doing. If we're looking for delta G naught at standard conditions, then we want to use our E at standard conditions. If we're looking for something not at standard conditions, so under the conditions specified in part A, we just want to use not the not version, the not version, the non-standard condition version. Like before, our n or our z is equal to 2. We can use Faraday's constant. And the E naught, got to make sure we're using the E naught here of 0.32. And when we do that, we come out with negative 61.75 kilojoules per mole. And if we do the same thing, but instead for E, use the actual E, the non-standard conditions E, then our delta G value comes out to be negative 54.42 kilojoules per mole. Does this make sense? Should we have a technically higher, but a less extreme delta G than delta G naught? Yeah, we talked about before that this cell is starting to get tired. It's starting to lose its forward capacity. So as a result, our delta G should be less negative than if all of the concentrations were straight up equal to 1. If you want more of this kind of practice, then I recommend checking out the 2019 exam, part 3, question 2. But we are going to continue on. We are going to just briefly see this idea that delta G is the same thing as electrical work. I would be really surprised to actually see this asked. So we're just going to continue right on and not worry. Now we're going to get into a special type of cell, and this is called a concentration cell. So you really got to focus on this one. Oh, goodness. I wish I had better jokes. If I had better jokes, then I'd tell you them, I promise. So a concentration cell is when you have the exact same reactants and products in both sides, but they are going to be different in terms of their usually concentrations and sometimes different in their partial pressures. So our E naught for a concentration cell is always going to be 0. Because if you had the exact same stuff in both sides, like you can't poof energy out of nothing, right? Could, then I think a lot of engineers would be out of the job if you could just poof energy out of nothing. That'd be pretty nice for everybody except electrical engineers. So, well, the difference, what's actually going to be generating our potential is going to be the fact that there will be different concentrations. And if we want to, we can relate this to the next equation. You don't need to write this down if you don't want to. I mean, that's true for literally everything I write. I'm not the boss of you. But the point is, if E naught is 0, then all of the E, all of the potential that we're seeing is coming from this Q term. So it's coming from that difference in our reactants or products. Now, sometimes you'll be asked something somewhat trivial about this type of thing. So you might be asked, what reaction is happening on the left? You think you can figure that out? There are a couple ways to do it. You've got 30 seconds to think it through. All right. So what's going to happen on the left? I'll tell you that typically the anode is written on the left. And an easy way to remember that is that it is the same as your shorthand cell notation. So also anode on the left, cathode on the right, but also it's alphabetical. So we could say the anode is the site of oxidation, and then we just pick the oxidation reaction. But let's imagine we didn't know that. Instead, what we would do is we would say, okay, what does this left side have more of? What does left have excess of? When we compare it against the right cell, we see that it has more chloride. And if we want to really drill this home, we would also say it has less Cl2. And what do you think this means? We can kind of treat these cells as if they're humans. If I have all hot dog buns, if I have lots of hot dog buns but no hot dogs, I'm going to try to trade, right? I'm going to trade some of my hot dog buns for hot dogs. So if this thing has lots of chloride but not much chlorine, it's going to try to use some of its chloride to get chlorine. As usual, we balance atoms, then we balance charges, and we are off to the races. Okay, let's really drill this home. So let's look at our development questions. Question 4. Super, super typical kind of question. Give this a read, give it a go. Part 1, good luck. Put a couple hints up there. Please let me know when you're done. All right, I've put a couple other hints up here. This is our last round of hints. We had to flip the reaction in blue here, the reaction involving iron, because we needed the iron 2+ on the reactant side. We also need to make sure that we're going to have electrons on opposite sides of these arrows. So the electrons up here are going to be on the left side, the electrons over here, a little bit hard to see because they are not aligned very well, but they are on the right side. Okay, so what do you wind up with as your E0? What do you wind up with as your Z? Those are always the two hardest parts. See if you can wrap this question. You've got a minute left. All right, let's wrap this up. So we're going to add up our E values here. And when we do that, we come out with 0.992 volts. All right, lovely. What is our Z value? Our Z value is going to be 2. It's going to be 2 because we're going to have to multiply this whole thing by 2. And that will allow these two things, these two sets of electrons, to cancel. So now we can sub all of this in. Oh, sorry, excuse me. The way that they've written this out is as a half. So we are not going to be multiplying this by 2. We're going to be multiplying this one by a half to get how they've actually written out this reaction. So as a result, the number of electrons flowing is going to be 1, just 1. Definitely tricky. Okay, so then we have 1 mole of electrons times 96485 times our E naught, 0.992, all over our R, 8.314, and times our temperature. Now, they often are a little bit lazy about talking about temperatures, so if that's the case, just use room temperature. And we come out with 6 times 10 to the 16, a gigantic equilibrium constant. And that's actually okay. Equilibrium constants can span a huge, huge range. I will also say that depending on like your exact rounding and all that kind of stuff, this number can vary a fair bit. So if you got like 5 times 10 to the 16 or 8 times 10 to the 16, that's all fine. They give you a bit of leeway on this one. All right, for question 2, we're not going to do all of question 2 because I think we probably have a good handle on most of it. But I just want you to figure out the second part. Which way is the current going to flow? Good luck. All right, friends, rocking it, rocking it. Which one do you think is going to be using zinc 2 plus as the reactant? The one that has lots of it or the one that has not much? The one that has lots of it. So on the left side, you're going to have zinc 2 plus as the reactant. And we see that it's going to be forming zinc solid. So we write zinc solid. And we need to balance with some electrons. So you know the drill. We've got a couple electrons on the left. So that means the left is consuming electrons. And as a result, the electron must be flowing toward the left. Lovely, lovely. So that is our final answer here. All right, we are starting to get into the end game here. And I know that some people have some scheduling conflicts, so I just want to take care of a couple things now. Thing number 1 is remember, if this is feeling overwhelming, in the next couple days, I will be sending an email with like probably the top 10 most important things to know. I've been highlighting them as we've been going through, but let's face it, that's hard to all remember. So top 10 things to know and top most important questions that will test whether you know those things. I got some good feedback about that from the midterm, so I'm going to be doing it again. The second thing is I want to know how your experience here has been going. I care a lot about this, and frankly, the number of very satisfieds is what keeps me employed with CourseCram. So please take a minute or two, let me know how your experience has been, and if you have any suggestions for how we might change things in the future. I'm going to put 2 minutes on here. Please fill out that survey. I've just thrown it in the chat. All right. Presumably, thanks very much. And now let's get back to it. We're heading back into our course booklet, and there are a few practice problems here, but I'm getting the sense that we're probably doing okay for those. So please join me now on page 62. Page 62. Now, this harkens back to a question that we started a while ago, and we're finally going to be able to wrap up. So we know that water is somewhat reactive. We know that it can break. That's what we talked about when we looked at the question on page 25, when we listed all of the possible reactants, and we included water as our possible reactants. But here's the thing. This question did not ask us to predict the products of electrolysis under standard conditions. It was a little bit sneaky. This 1 molar would probably make us about standard conditions. But are the concentrations of lithium and bromide the only concentrations that matter here? There are actually other concentrations that matter too. Because if we look at our oxidation and reduction reactions for water, we see we've got some other products here. Now, notably, the 4H plus and the 2OH minus, those are the things that matter. Reason being, this is telling us that how spontaneous these reactions are is actually going to depend on the pH. Now, I'd be a little bit surprised to see if you were asked like something that was really, really quantitative here. The idea is that this reaction, that oxygen plus 4H plus 4 electrons is at equilibrium with 2H2O. The idea here is that as we decrease the pH, what's that doing to our concentration of H+? As we decrease the pH, we are increasing the concentration of H+. And if we're increasing the concentration of H+, we are shifting this reaction forward. So as we decrease the pH, we are making this reaction more spontaneous. And as we increase the pH, what are we going to be doing to something like this? As we increase the pH, what's that doing to the concentration of H+? It's going to be decreasing that, shifting this to the left, and therefore, it's going to be making this reaction less spontaneous. Now, again, frankly, I'd be a little bit surprised to see this in any kind of like really quantitative way. The way that I would expect to see it is pretty much as we see it with knowledge development question. So how do we do this? We think about at pH 7, what does that mean for our concentrations of these things? At pH equals 7, the concentration of H+ is going to be 10 to the negative 7. And the concentration of OH minus, hopefully you guessed it, is also going to be 10 to the negative 7. So these are both going to be really low. What does that mean for the E here? Our E naught is this and this, but is our E going to be bigger or smaller? Let's choose, which one do we want to choose here? Let's choose the oxidation one. So let's choose this top one. Is our E of oxidation of water going to be bigger or smaller than our E naught of oxidation of water? Well, the concentration of our product is really low. And then, therefore, based on Le Chatelier's principle, this is going to shift this reaction quite hard to the right. So that's our kind of like hand-wavy explanation. If we really wanted to work this out completely, we could use something like the Nernst equation. And what would we have in our lawn here? Try to write out the Q for this oxidation reaction. Okay, so the Q for this oxidation reaction is going to have our concentration of O2 and our concentration of H+. That's going to be to the 4, so that's going to really dominate things. And this is going to be so small. How is that going to work out mathematically? ln of a very small number, let's say like 10 to the negative, I don't know, a bajillion. If we actually did this, 10 to the negative 1428 or so. Try doing that and see what you get for your E. Remember, your E naught is up there at negative 1.229. Okay. So when we do that, and we have our T over NF, ln of that huge thing, we come out with an E of negative 0.82 volts. So what this is telling us is that this is actually now going to be a higher number than the E naught for bromide. And remember, we're dealing with negative numbers here, so higher number means less negative. This is less negative than negative 1.065. Let's be very clear where we got that from. So do you remember how we chose which one we were going to use here? We were selecting the less negative values. So under standard conditions, yeah, these two would be happening. But under the conditions that the question actually specified, the water is going to beat out the bromide. And as a result, under the question's conditions, the oxidation reaction is going to be the water one. The water one now wins. And therefore, our products are not going to be these anymore. Now, our products are going to be H2 and OH minus, so that one has stayed. But we're also now going to be producing oxygen and H plus. And as usual, if we're producing both OH minus and O and H plus, those are going to cancel. So the answer to this question after all of that is just H2 and O2. Yeehaw. What a question. Oh my goodness. All right, let's pop back into our booklet. And I would say we are pretty much done the tough stuff now. Because everything else is, I'd say, a little bit easier or kind of applications of what we've already seen. We've already done that question, so that's great. Just as an aside, sometimes you might be asked about overpotential. These just mean that the E naughts go up a little bit, but you don't need to know anything specific about it. In the question, they'll say like the E naught is 0.15 volts higher or something, and then you literally just add it. I'd be a little bit surprised to see that on the exam, so we're just going to continue on. Now I've got a handful of batteries to show you, though, again, I think this stuff is pretty low priority, so we're kind of going to skim through them. At worst, I think you might have to, being given this kind of thing, you might have to like write out the reaction that could occur, or you might have to write like the shorthand cell notation, something along those lines. It would be the worst case scenario here. So let's just do that in detail for one of these, and then we'll kind of skim through the rest. This question asks, what are going to be the reactions and overall standard cell potential for this battery? So what do we even have reacting here? We have MnO4, we have ammonium chloride, we have zinc chloride, and we have water. Okay, so it's not really obvious which of those are going to be important. The reason why we're essentially doing this question is so that I can just point out that they are being a little bit stealthy and telling us we have this zinc can as an electrode, which means we also have zinc present. So what we want to do is we want to look at our standard cell potential, or our SRP table. Let me just copy that back over here. And we essentially want to just figure out like which of these is likely to react. Which of these wants to react a lot? So do we see, we've seen zinc a few times, so let's just put a little pin in zinc there. We've seen manganese oxide. Oh, actually, that's a different version. Manganese oxide would be that one. That's the one that someone had a question about earlier. Do we see any NH4 plus? I don't see any NH4 plus, so it's probably not important there. Do we see, we have Cl. Do we see any Cl minus? There's probably some Cl minus somewhere around here. Where are you, Cl minus? You should be up here somewhere. There you are. But we don't have chlorine gas. We have Cl minus. So we would have to put a negative sign on that. And negative 1.36 volts, that like really doesn't want to react. So it's probably going to be our most reactive thing. And then also, in addition to having zinc solid, we have zinc 2 plus. So we find zinc 2 plus, and we see that there. What is the relevant E naught for zinc 2 plus? It's going to be negative 0.763. That's also pretty low, so it's probably not looking good. For our manganese oxide, our MnO, that is probably going to react. Like that's 1.23. It's a positive number, always a good sign. And for zinc, what about it reacting? Well, for zinc, we would need to flip this. So we would have positive 0.763. So as a result, we now know our two reactions. Our two reactants are going to be zinc and manganese oxide. So what I'd like you to do is please write down the overall reaction and give the overall E naught. Good luck. All right, let's take a look. So our overall reaction is going to be the sum of a couple things. MnO4, MnO2 rather, plus 4H plus 2 electrons goes to and returns from Mn2 plus 2 H2O. And that has an E naught of 1.23 volts. And what about the other one? That's going to be zinc. Zinc going to and returning from zinc 2 plus and a couple electrons. And that is going to have an E naught of, remember, we got to flip the sign, 0.763. And as a result, when we add those two things up, we get 3991. So we get a voltage that's pretty close to 2. All right, so once again, how do we do this? We look at all of our potential reactants, and then we choose the ones that are the most positive for the reduction and most positive for the oxidation. If this sounds familiar, if this sounds like exactly what we did for electrolysis, then you are correct. It's the exact same type of idea. In both cases, what you're looking for is just what wants to react the most. Okay, so we are not going to go through the exact same type of thing with these other ones. I think they're just kind of the same thing over and over and over again. One thing that I am going to highlight here is a fuel cell. A fuel cell, it uses, believe it or not, a combustible fuel. It uses fuel. And we can use either hydrogen or methane or really kind of like anything that's combustible, but just for, we tend to use nice simple ones. And the important part about a fuel cell is that you have this fuel flowing in or out. And as a result, when we think about our Nernst equation, how is Q going to change over time? Q is not going to change over time because the concentrations are roughly constant. Because you constantly have new fuel coming in and excess fuel pumping out, As a result, if the Q is constant, then the voltage is also going to be constant. And this is obviously very useful, right? Imagine if you had to run electronics with things with constantly fluctuating voltages, it would be a bit of a problem. So now finally, there are some conceptual kind of philosophical things about corrosion and about protection. So corrosion is obviously really important for structural and mechanical engineers. And it's all about this really nasty reaction, which is iron oxidizes. It rusts. And iron is really nice and structurally sound, and rust is really not structurally sound, obviously. I mean, I know who I'm talking to here, so you know this. So there are a few different ways that we can deal with this. We've got 3 ways that we can potentially fix this problem. So the first one is with a coating, because if this reaction is to occur, these electrons need to go somewhere, right? It's called redox for a reason. This is oxidation, so it needs a reduction partner. And one option is just to say, no, I refuse to let you have a reduction partner. You just completely seal off your iron from the rest of the universe. You have some kind of amazing coating here. And if you have this amazing coating, then there's not going to be any partner reduction reaction. So great. And this sounds like it's really demanding, but like paint is actually really good at this. And that's actually why, you probably know this too, but that's why they are constantly painting bridges. The idea is that bridges are made out of mostly iron, usually iron and carbon, steel, of course. And as a result, if you cover the iron, if you cover the steel, then you're not going to have any oxidation taking place. But this is why people will be painting a bridge, and they just paint these bridges every day. So you start on one side, you paint and you paint and you paint and you paint and paint, and it maybe takes the painters a year to paint the entire bridge. And by that time, the beginning needs a fresh coat of paint. So you paint and you paint, and there are people who just make a living painting bridges, like the same bridge all the time. The problem is what happens if this coating breaks? So there are 2 problems here. Problem number 1 is the obvious problem, which is, all right, if this coating breaks, then oxygen, which of course is a good oxidant, oxygen can get in there on the substrate, and now you've got rust. The bad part about this is that, like the even worse part about this, is that once you have a break over here, now the coating, which has this kind of outward force, now this coating is more likely to break in other places. So once you have a chink in the armor, other parts of the armor become less and less stable. And now you've got this positive feedback loop where you just get rust everywhere, and it's very sad. Okay. So that's one way of dealing with things. And as I said, it's like kind of demanding, but as long as you don't care about like everything being absolutely perfect, you can make it work. Another one, and unfortunately iron doesn't work well with this, but aluminum does, is what if the thing just automatically had a protective coating? So let's look at aluminum for a second. And let's consider its SRP. So where do we find aluminum here? We find it here. And if we're using aluminum as a reactant, we would have to flip this. To give us aluminum 3+ and 3 electrons. And its E naught is gigantic. 1.662. That's not an overall E naught, that's just a straight up E naught. So that thing is huge. That tells us that aluminum is super, super ready to get oxidized. And in kind of a funny way, its eagerness to get oxidized is part of what makes it so stable. Because immediately, within like fractions of a second, you get this what's known as a passivating layer. And this passivating layer is aluminum oxide, also sometimes called alumina. And the amazing thing here is that aluminum oxide stops oxygen permeation. And what that means is that our oxidant now, our oxygen, it just kind of bounces off the aluminum oxide, because aluminum oxide is super, super stable. It's not good mechanically, like it's kind of frail, like you can scrape it off a little bit. But the nice thing is that it completely stops oxygen. So this is like a self-painting material. And if you ever get any kind of gap, let's say someone like takes an X-Acto knife and just like cuts your aluminum oxide, it totally doesn't really matter because the aluminum underneath is just going to immediately generate another layer. So it's amazing. Now, of course, the drawback with aluminum is that it is not particularly structurally sound. It's very chemically sound once you make this, but it is not very structurally sound. So like making skyscrapers out of aluminum is going to be a tough call, tough job. So our final one, and this one is, I would say, the focus, is what's known as a sacrificial anode. So what happens here is you have something else that is going to oxidize more easily than iron. So let's look at our iron here. Our iron is this one, 0.44. And let's imagine that like we're doing a pretty good job of blocking any oxygen, but we're worried that there's going to be a scratch somewhere or something like that. So we want a backup plan. And in fact, usually a sacrificial anode is going to be a backup plan. It's often used in combination with other techniques, usually painting. So you've painted the thing, but you're worried like someone's going to come along with an X-Acto knife, or maybe just there'll be some wind and sand will scrape some stuff, some paint off or something like that. You know, life happens. So what you're going to do is you hook up your thing that is going to much more actively oxidize. So aluminum might seem like a good option for this, but as we saw before, aluminum actually generates that passivating layer. And what that means is if you tried to use aluminum for this, it would immediately develop some aluminum oxide there. Aluminum oxide is not a conductor of electricity, so now you've just like cut off your system, and that's going to be no good. So what you need is something that doesn't immediately develop that kind of thing, something that is better able at keeping that conductivity. And something like magnesium is actually a pretty good option here. Now, sometimes I've seen instructors ask, like, which of the following could be a sacrificial electrode for iron? How would we decide that? Which could work? What you want is an E naught that is higher. And remember, you need the metal as the reactant. So let's again look at our lovely reaction here. So between lead, actually I'll use tin. Between tin and zinc, I'm going to use the lower one. Let's use, now I do want to use zinc because zinc is also kind of popular. Which one of these is going to be a potentially useful sacrificial anode? It's going to be the zinc. Because remember, we need the metal as a reactant, so we're going to have to flip all these reactions. For zinc, that's going to get 0.763. For tin, that's going to get 0.137. So this one is going to be more reactive than iron, whereas tin would be less reactive than iron. Okay. Finally, let's look at galvanization. This is kind of a combination of these two things. So we're going to coat the stuff that we care about protecting in a sacrificial anode. And a common way of doing that is with zinc. So you coat this thing with zinc, and now what happens? What happens if some sand blasts away your zinc? Well, if that's the case, it's not the end of the world, because this can still act as a sacrificial anode. So it does two things. It's a coating and a sacrificial anode. All right. So congratulations. You have made it through. You have gotten through all of the content. Amazing. We're going to do just another 1 or 2 questions to wrap this up. We're going to go to our knowledge development stuff. And let's look at question 20, or let's look at page 28. What I'd like you to do is please consider questions 2 and 3. You've got a couple minutes on this. Let me know when you're done. Good luck. Seeing some dones trickle in here. You have 1.5 minutes remaining. All right, let's wrap this up. They tell us coating iron with a thin layer of zinc metal is galvanizing. How does this help even when the coating is damaged? So, number one, it helps prevent oxidants from, did they say iron? Yeah. From getting to iron. That's the first part. But the heart of their question is, how does it work even when the coating is damaged? It's going to work even when the coating is damaged because zinc can be a sacrificial anode. And then how do we know that? It can do this because it reacts more readily, more spontaneously with something trying to oxidize it than iron does. The relevant E naught for zinc we would find here at 0.763. And for iron, we've seen that one a few times now, it is 0.44. Once again, we're flipping those because we need to make sure that we have the metal as the reactant. All right, so then looking at 3, tinning is where a thin layer of tin metal is deposited on this metal surface. But for this, does the protection continue if the surface is scratched? So first of all, how does it protect? Exact same type of idea. Prevents oxidants from getting to that. But now part 2 is a completely different answer. Because tin's E naught is going to be that 0.137 volts. This is less reactive to oxidants. Therefore, it provides no protection after damage. All right, friends. You did it. You got to the end of this. I hope this has been super, super helpful. As I said, I'm going to send out those like top most important things to know for if you're feeling overwhelmed, and that will include the pre-midterm material. As a little spoiler, you are almost certainly going to see a question about buffers. I'm going to turn this over now to the Q&A. If you're not sticking around for the Q&A, that's totally fine. I hope you have a splendiferous rest of your day. Now looking over at the Q&A. Oh, and also remember, if you have any other questions, feel free to post in the Facebook group or send me an email. And as a reminder, that email is mikemchem@gmail.com. Thank you. You're welcome. Hope this has been helpful. Hope you absolutely ace your final exam. This course has definitely been really something this semester, especially with the lack of relevant practice problems they've been given. So I'm trying really hard to fill in that gap. Right, currently not seeing anything in the Q&A. So this is your last call. If you're in the middle of typing something, please click submit so that I know I should continue waiting. All right, seeing nothing further, I'm going to call it here then. Hope y'all had a lovely time. Hope y'all have a lovely life, and hope y'all absolutely ace your exam. Take care.